Hello everyone. In this video, we will learn how to explain the meaning of Heisenberg's uncertainty principle and demonstrate how such uncertainty limits our knowledge of electron properties. To apply the uncertainty principle in calculations to demonstrate that the location and velocity of a subatomic particle cannot be determined simultaneously and accurately. Let us start with the definition first. Heisenberg's uncertainty principle states that it is impossible to know accurately and simultaneously both the position and momentum of a moving particle. In other words, the more certain you are of an object's momentum, the less certain you are of its position, and vice versa. Mathematically, the Heisenberg's uncertainty principle is represented by the following equation. Delta x times delta p is greater than or equal to h over 4 pi, where x is the position of the particle and delta x is the uncertainty in its position, p is the momentum of a particle and delta p is the uncertainty in its momentum, and h is the Planck's constant. As we learned earlier, momentum of a particle p is equals to its mass times velocity. Therefore, we can write delta p is equals to delta mv. Mass of the particle remains a constant, or uncertainty in its mass is 0. Therefore, we can write delta p is equals to m delta v. So, we can also write Heisenberg's equation as the following. Delta x times m delta v is greater than or equals to h over 4 pi, where v is the velocity of the particle and delta v is the uncertainty in its velocity, and m is the mass of the object. So we can also state Heisenberg's uncertainty principle as it is impossible to know accurately and simultaneously both the position and velocity of a moving particle. Let us take a closer look at the equation and understand what each of these terms mean. Let us say you are standing at a signal to cross the road and a car is moving towards you. At a particular instant, the car is 20 meters away from you and traveling at 60 miles per hour. According to Heisenberg, there is inherent uncertainty both in the position and velocity of the car. This uncertainty is not because of a measurement, but it is inherent uncertainty associated with the car. For example, if we are saying that the uncertainty in the car's position is 1 meter, that means the car could be anywhere between 19 meters and 21 meters from you. In fact, according to Heisenberg, there could be several cars that can exist between 19 meters to 21 meters. Similarly, if we say that the uncertainty in velocity is 5 miles per hour, then the car could be traveling anywhere between 55 miles per hour and up to 65 miles per hour. And there could be several cars, each of them traveling at different velocities within that range. This idea is so counterintuitive when you apply it for the real world around us, but it is quite appropriate for the quantum world. Let us say delta x is equals to 0, meaning the uncertainty in its position is 0, or in other words, we know exactly where the particle is. Then, according to the equation, delta v becomes infinity, which means the uncertainty in its velocity is equal to infinity, or in other words, we have no idea of particle's velocity. We can do the same thing with velocity. That is, if delta v is equals to 0, then delta x becomes infinity. This is how the equation defines Heisenberg's uncertainty principle. Just like the de Broglie's wavelength, Heisenberg's uncertainty principle is applicable only for microscopic particles like electrons and protons, and it becomes insignificant for macroscopic objects like football or a car, etc. In the next couple of slides, we will understand why. Let us say we apply Heisenberg's uncertainty principle on a macroscopic object which weighs 1 gram. Delta x times m delta v is greater than or equals to h over 4 pi. We can rearrange this equation and write delta x times delta v is greater than or equals to h over 4m pi. Plugging in all the values, we get 6.626 times 10 to the negative 34 kg meter square per second divided by 4 times mass, which is 1 times 10 to the negative 3 kg times 3.14. If we do the math, we get the following. Delta x times delta v is greater than or equal to 5.28 times 10 to the negative 31 meter square per second. The minimum amount of uncertainty in the product of position and velocity is an extremely small number. Let us say this 1 gram object is thrown at something, and the uncertainty in the position of this object at an instant is plus or minus 1 centimeter. That is, the object can be anywhere between these limits. Then, the minimum uncertainty in its velocity becomes delta v is greater than or equals to 5.28 times 10 to the negative 31 meter square per second divided by delta x, which is 0.01 meters. If we do the math, you would get 5.28 times 10 to the negative 29 meters per second. The minimum uncertainty in its velocity is an extremely small number. It is as if we know the exact velocity of the football. Therefore, we can say that the Heisenberg's uncertainty principle is insignificant for the macroscopic objects. Now, let us do a similar kind of calculation for microscopic objects such as an electron. For microscopic objects like electron, the big difference is its mass. The mass is an extremely small number. For electron, this number is equals to 9.11 times 10 to the negative 31 kilograms. The Heisenberg's equation is delta x times m delta v greater than or equals to h over 4 pi. If we rearrange this equation, we get delta x times delta v is greater than or equals to h over 4m pi. Plugging in all the values, we get 6.626 times 10 to the negative 34 kg meter square per second divided by 4 times 9.11 times 10 to the negative 31 kilograms times 3.14. If we do the math, we get delta x times delta v is greater than or equals to 5.79 times 10 to the negative 5 meter square per second. The minimum amount of uncertainty in the product of position and velocity of an electron is not that small. Let us say we know the position of the electron inside a hydrogen atom to an accuracy of 1% of the hydrogen's radius. The radius of hydrogen atom is 0.05 nanometers. Therefore, the uncertainty in the position of the electron is 0.0005 nanometers. What this means is that if we assume the three-dimensional space around the nucleus of hydrogen is broken down into several concentric spheres of increasing radius, we know that the position of electron is somewhere between the 99th sphere to 101st sphere. Let us now plug in this delta x value in the above equation. Delta V is greater than or equals to 5.79 times 10 to the negative 5 meter square per second divided by 0.0005 times 10 to the negative 9 meters. If we do the math, we get delta V is greater than or equals to 1.16 times 10 to the 8 meters per second. The minimum amount of uncertainty in the velocity of an electron is an extremely large number. If you can identify, it is of the same magnitude as the speed of the light. This amount of uncertainty means we can safely say that we have no idea of the velocity of the electron. In summary, if we know the electron's position with a minimum uncertainty of 0.0005 nanometers, then the uncertainty in the velocity of the electron is at least 1.16 times 10 to the 8 meters per second. This is what exactly the Heisenberg's uncertainty principle states. Next, we will discuss the significance of Heisenberg's uncertainty principle. In other words, what it means to the model of atom that we have been discussing so far. One of the implications of Heisenberg's uncertainty principle is that it rules out the existence of orbits with specific radius for electrons. Let me explain why. If we know the exact position and velocity of the electron at any instant and all the forces that are acting on the electron at that instant, we can predict where the electron would be after some time t. This is what we call as the path or orbit of the electron. But according to Heisenberg's uncertainty principle, it is impossible for an electron to have a precise position and velocity at any given instant. Therefore, it is not possible to talk about specific paths or orbits for subatomic particles like electrons. So, if we don't know the specific orbits or paths of the electrons, then where is the electron inside the atom? We use something called as probabilities to express the position of an electron. We draw a sphere around the nucleus of a hydrogen atom and say that the probability of finding the electron inside the sphere is at 99%. We cannot say where exactly the electron is inside the sphere, but we can say that 99% of the times it is inside the sphere. Applying this to our analogy, we cannot say that the car is exactly 20 meters away from you, but we can say that the probability of finding the car from 19 meters to 21 meters is about 95%.